Okay, hi, welcome to our next Tropical Forest Ecology and Use lecture, Changes in Tropical Ecosystems over Geological Time. In this lecture, I hopefully give you a history of tropical rainforests and to a lesser extent tropical dry forests and tropical savannas as they changed over geological time. Since the origin of tropical rainforests. So I want to talk about the origins of rainforest and how that rainforest has changed through time, looking at some of the different periods, the origins of the tropical rainforest in the Cretaceous Period, about 100 million years ago, the Tertiary Cooling, and the ice ages which continued from the Tertiary into the Quaternary, and finally I want to take a look at some of the implications for the current state of tropical ecosystems that we see today, and in particular the implications for management of those tropical forests and tropical ecosystems. And yes, there are implications even today of what happened back in the Cretaceous or the Quaternary millions of years ago. So first of all, I'm going to start with the origins of the rainforest. Just to point out first of all that the textbook Tropical Rainforest Ecology, Diversity and Conservation by Ghazul and Scheel has a good account of the history of rainforests. Now, in this lecture I'm going to concentrate mainly on the flowering plant rainforests that we know today, although Ghazul and Scheel in their account really look at forests and how forests have evolved and the history of forests in the geological record through time. But I want to concentrate on tropical rainforests as we know them today, which are dominated by flowering plants or angiosperms. Prior to the Cretaceous, about 144 million years before present, ferns and conifers and lower plants dominated the terrestrial ecosystems on this planet. At the beginning of the Cretaceous, conifers were the dominant tree forms on many of the terrestrial ecosystems around the world, with pteridophytes, ferns and cycads. You see a picture of a cycad down here, a zamia palm, dominated the understories of these coniferous forests. Now these coniferous forests were closed canopy, and they eventually evolved by the beginning of the Cretaceous into many warm, wet, rainforest type climates pretty much all around the world. Okay? But by the Cretaceous things began to change, and in particular the angiosperms first appeared. So K is the Cretaceous, and the start of the Cretaceous was about 144 million years ago. At that time, gymnosperms dominated the flora of the earth. So this is that familiar graph that I've showed you before, how terrestrial plant species have changed over geological time in the fossil record. At the start of the Cretaceous, pteridophytes were very much present, along with the gymnosperms, which dominated, and they formed most of the forests. But in the first half of the Cretaceous, the first confirmed angiosperm fossils were identified, and from those first fossils until the end of the Cretaceous, the angiosperms rapidly diversified, and many of the families of flowering plants that we know today were established by the end of the Cretaceous. By about 90 million years before present, angiosperms tended to dominate the world flora as they do today. So by the end of the Cretaceous, the angiosperms basically dominated the rainforests around the world. And this is sometime in the second half of the Cretaceous. So by the end of the Cretaceous, angiosperms were firmly in place as the dominant plant group on land, and they dominated the warm, wet climates which rainforests occur in today. So effectively we can say that tropical rainforests first arose during the Cretaceous period, and by the end of the Cretaceous, or 90 million years in the Cretaceous, they dominated much of the warm, wet climates that we know today. There is a certain amount of conjecture and speculation over the different families or the different groups within the flowering plants and when they arose and so on. A lot of these plants, these groups, these families of flowering plants, tend to be these days restricted to certain parts of the tropical world. So for instance, the Proteaceae tends to be restricted to southern hemisphere ecosystems and southern hemisphere rainforests. It dominates the ecosystems of Australia. There are many different Proteaceae, but in the neotropics they are restricted to only a couple of species. So this Proteaceae is thought to be a family which arose after the splitting of continents of South America away from Antarctica and Australia, and therefore the Proteaceae does tend to be more of a Antarctic Australian family rather than a pantropical family. An example of a pantropical family may be the Meliaceae. The Meliaceae includes many of the timber trees that we value today, including mahogany and cedar, and also crapo. The Meliaceae is found all around the tropics, in both the neotropics. It's quite a common group, also in the Australian tropics and in the African tropics as well. So this group may have arisen before the split up of all the continents. It's thought that the continents began to split up about 100 million years ago, around about the time that the angiosperms started to diversify. However, it has been found that current day distributions of tropical plants aren't really a good indication or a definitive indication of where these plants actually came from. For example, some plant families which are found in the neotropics and are actually shown in the fossil record to have actually originated in the paleotropics in East Asia and Australia, and they've made their way to the neotropics via land bridges sometimes through Asia and North America, and then down through the Panama Isthmus when it was formed, or even through the Aves Ridge connection island arc when that was above water, and subsequently they have gone extinct in Asia and Australia, so the only representatives left now are in the neotropics, but their origin was actually in the paleotropics. So current distributions are by no means definitive of the origins of these species and when and where they evolved. So we need to be very careful. In the past, current distributions have been used a lot, but with development of molecular techniques and more fossil evidence being found, people are becoming increasingly aware and of the opinion that these current distributions are not definitively reflective of origins, points of origins or areas of evolution of these different families. So by the end of the Cretaceous, I think this map is representative of distributions of different tropical ecosystems by the end of the Cretaceous. As you can see, the black is tropical rainforest. You can recognize most of the continents. Some of the continents are in pretty much the same position as they are now. South America is a little bit south of where it should be. India hasn't made its way and collided with Asia as yet. Australia has not split off from Antarctica yet and is still in a very much more southern position. Okay, but we have the equator here to give us an idea of where the latitudes are, and the polar regions are obvious in these areas here. Okay, so tropical rainforests these days are pretty much restricted around the equator, but as you can see at the end of the Cretaceous, the black tropical rainforests extended all the way up to almost the boundaries of what we would consider the boreal forest today, and even beyond these boundaries we had paratropical rainforests. So these would, I guess, maybe be subtropical rainforests, and beyond that you had evergreen broadleaf forest, and beyond that you would have polar broadleaf deciduous forest. So you would have your drier forests, and then maybe your tundra very much restricted to immediately around the poles. So this reflects a much warmer and wetter world back in these days, and we'll see an average temperature graph later on. So actually let's see if we can see that now. So 65 million years ago, that's the end of the Cretaceous. At the end of the Cretaceous there, the average global temperature, so the average temperature across the surface of the globe was about 26 degrees Celsius. So if we compare with today's average global temperature across the surface of the globe, it's about 14 degrees Celsius. Okay, so it's a massive, the average global temperature was much higher at the end of the Cretaceous compared to where we are today. Okay, so tropical rainforests spread almost to the poles. Okay, and this was the ecosystem when flowering plants diversified very rapidly, and that's a bit of a mystery to most scientists, how angiosperms were able to rapidly take over what were gymnosperm dominated forests so quickly. Okay, within a couple of million years from their first appearance, angiosperms rapidly colonized and overtook and dominated most of the terrestrial ecosystems on Earth at the time. So at that time, tropical rainforests, as represented in this picture, dominated most of the Earth. I've got a picture of a magnolia here. The magnolias are thought to be one of the first flowering plant families. So that was one of the basal, as they call it, one of the ancestor families of flowering plants. So they were probably well represented throughout these flowering plant rainforests which arose during the Tertiary. the Cretaceous. And here is another representation of the land areas which were thought to be present on the Earth at that particular time. So you can see Africa there. Northern part of Africa is thought to be underwater. Most of Europe is underwater. South America is there. Antarctica with Australia joined on. Asia looks like it comes down much further than it does today. Okay, but the thing to note is flowering plants came to dominate tropical ecosystems very quickly, and by the end of the Cretaceous they dominated pretty much all the tropical ecosystems. And unlike today, tropical ecosystems spread from the equators almost to the poles, so they had a much wider distribution, indicating the Earth was much wetter and much warmer than it is today. Okay. Just a little time check here. Cretaceous, 144 million years to 65 million years. By the end of the Cretaceous, at about 65 million years, there was tropical rainforest almost to the poles, and that tropical rainforest was dominated by angiosperm families or flowering plant families. Most of those families we still see in tropical rainforests today. So most of the families of tropical flowering plants, rainforest tropical flowering plants, we see still around today. Okay. Another point to note also is that these tropical rainforests of the end of the Cretaceous were dominated by flowering plants and covered most of the surface of the Earth. Therefore, pretty much all of the temperate ecosystems that we see today, which are dominated by flowering plants like deciduous forests and savannas and deserts and temperate forests, okay, they all of the species, all the flowering plants, have their origin in a tropical rainforest. Okay, so all of these flowering plants in deserts, in temperate forests, and in savannas or temperate grasslands, all of those species, their ancestors arose first in a tropical forest. So tropical forests were the origins of many of these species. Other ecosystems like the boreal forests, which are dominated by conifers, probably had their origin in more ancient ecosystems. Right, so the Tertiary started about 65 million years before present with a bang, literally, because this boundary between the Cretaceous and the Tertiary is known as the KT boundary, and it's very famous for the extinction of the dinosaurs. It's characterized all around the world by a thin layer of iridium, which is taken to be evidence of the impact of a extraterrestrial meteor impacting somewhere on the surface of the Earth. Fossil evidence indicates that for about 2 million years after that event, tropical forests were devastated and destroyed, and the terrestrial ecosystems were dominated by small shrubby fern flora. After about 1.5 million years, the angiosperm rainforests recovered, and by about 2 million years before present, they were back to pretty much their former extent. So there was a bit of a blip there at the Cretaceous Tertiary boundary, caused by an extraterrestrial impact. So for about 1.5 million years, the global ecosystems were disturbed, but after that they returned to pretty much what they were like before. Okay? It's thought that no deserts or savannas existed. However, I have just read that dry forests were thought to exist. Probably not angiosperm dominated dry forests. They may have been conifer dominated dry forests, but generally tropical rainforests were the rule. Rainfall and temperatures were high and constant over pretty much all of the surface of the globe. Okay, and pretty much with the start of the Tertiary, for the first 10 million years or so of the Tertiary, temperatures remained pretty much high. So for the first 20 million years of the Tertiary, remained pretty much high until around 50 million years before present. Okay, at around 50 million years before present, there was a sudden dramatic cooling in the global temperature according to the fossil record. And over the next 20 million years or so, the temperature dropped until around about 33 million years ago, the temperature was approaching the sort of average global temperature that we see today. The reason for this cooling is very hotly debated. Nobody really knows for sure why there was this sudden dramatic cooling in the average global temperature during the Cretaceous. There's been a few speculations and a few hypotheses proposed. My favorite is that tropical rainforests all the way up to the poles were incredibly productive, and so they sequestered huge amounts of carbon from the atmosphere, causing like a reverse greenhouse effect, which meant that global temperatures could not be sustained as the CO2 was taken out of the atmosphere, and the atmosphere became less of a greenhouse, and so the global temperatures fell. Okay, this reverse greenhouse effect has also been postulated for earlier on in the Earth's geological history, around the Silurian, Devonian. There were massive forests of pteridophytes and cycads, and during the Devonian there was a massive dieback of these forests, as with concomitant with evidence of increased glaciations and decreasing global temperatures. And it's thought that this period was caused by massive extraction of carbon dioxide from the atmosphere through the over-success of these terrestrial, very highly productive plant ecosystems, which basically pulled the CO2 out of the atmosphere through photosynthesis. Did the same thing happen in the Tertiary and led to the dramatic Tertiary cooling? Maybe so. Nobody really knows for sure. But what happened was the average global temperature fell from around 27 degrees Celsius all the way down to about 16 degrees Celsius, a massive fall. Along the way, the Antarctic and the Arctic ice caps were formed, okay, reducing sea levels, okay, and a mass extinction event which occurred during this cooling period finally ceased. Okay, as the climate looks like it began to stabilize. Okay, although it looking like it fluctuating a fair bit during the Oligocene and the Miocene. So, what happened to the tropical rainforests? Now, obviously, with this massive reduction in the average temperatures, tropical rainforests were not sustainable up in the higher latitudes. So tropical rainforests were basically devastated at the higher latitudes and disappeared, and were restricted to within 15 degrees of the equator. Okay, some of these ecosystems were taken over by conifers, and those are the boreal forests that you see today, and some of these ecosystems were taken over by grasslands. Some of the species within the rainforests were able to survive the cooling, and they evolved forms which could survive the cooler temperatures, mainly the grasses, and they formed large grasslands. Okay, rainforests were restricted to within 15 degrees of the equator, which is still greater than the area that we have today. Today we're within 5 degrees north or south of the equator consistently. Okay. During this period, forests become open plains, grasslands, and so on. Okay, so by the end of the Miocene, towards the end of the Miocene, about 10 million years ago, grasslands are fully developed in the interiors of continents and in tropical areas as well, where the rainfall is lower. Okay. Right, so tertiary cooling. I was watching this. Right, this is the current day situation, and this is the climate which is thought to have existed back in the ice ages, or the middle of the tertiary, when things tended to be cooler and drier. Okay, some of these continental positions are slightly different than we see today. For instance, Australia is further south than it was then, and sea level positions have changed and so on. As you can see, the rainforests tend to be more restricted during the ice ages when it's much cooler. Okay, and they are replaced by the light green, which is grassland or savanna, tropical savanna. Okay, tropical savannas tend to be much more widespread in Asia as well, in the temperate regions, and in North America. Okay, temperate forests tend to be more widespread as well. Okay, and temperate grasslands are much more further north than they exist today. Okay, so ecosystems or biomes have shifted around the world as global temperatures changed. Okay, and some biomes were even created during these tertiary cooling periods, which were well, it's not unprecedented in Earth's history, but very dramatic changes from what the terrestrial ecosystems evolved to cope with from the Cretaceous, from the beginning of the Cretaceous. So there was a massive change. Okay, right, let's move on now to the Quaternary. So the Quaternary comes after the Tertiary, and that's around starts around 2.8 million years before present, and it's characterized by another severe cooling, okay, during the end of the Miocene and into the Pliocene, and these are what we know as the ice ages. Now, there have been several dips in temperatures and oscillations in temperatures over the past 2.5 million years. Okay, so you can see the oscillation of temperatures. We get better resolution of temperatures during these periods because the fossil record is just so much better, because most of the deposits are still recent, so there is still a lot of evidence left. Okay, so this line represents the average global temperature today. Okay, 10, 11, 12, 13. So it's around 16 degrees Celsius. Okay. Yeah, so there's been a very strong oscillation of the global temperatures. Okay, so this has meant that tropical rainforests, the temperatures have always been fairly low, so tropical rainforests have been restricted to smaller extents than we see today during the height of these glacial periods, and then go back to pretty much the extent we see today, and then more restricted, goes back, more restricted, goes back to pretty much what we see today. And it's pretty much leveled off over the past 10,000 years or so. Oh no, probably over the past 10,000 years ago, which is the Holocene. Okay, H is the Holocene, so it's pretty much leveled off. Okay, so in the last 10,000 years ago, I think the last maximum of the glaciations was about 20,000 years ago, and temperatures have rapidly warmed and then stabilized over the past 10,000 years. Okay, with every cycle in the temperature, the tropical ecosystems will shift their boundaries. They will move to different extents and so on. And what I want to do now is to talk about how the boundaries of these tropical ecosystems have varied in comparison with their extents today. Okay. Right, in the tropical record, in the geological record, most of the attention of how glaciation affected the world tended to be restricted to temperate regions. And the reason for that is because the evidence is really just much more prominent in these temperate regions, because these temperate regions were severely affected and they were covered in glaciers. Glaciers are huge sheets of ice, and they leave a lot of evidence. Some of this evidence is glacial striations. So this is a rock, a piece of bedrock. Okay, and during the last glaciation, a huge sheet of ice was moving slowly across the face of this rock, and bits and pieces of rock carried in that ice would have been dragged across this rock face, causing these big long scratches or striations, and these are very evident. Okay, there are also landforms like U-shaped valleys and small cirques or tarns, or very rugged landscape which glaciers leave behind. And these are all traces that glaciers were in an area during the last ice age. Okay, there's none of these glacial traces in the lowland tropics, and it's only when people began to explore a bit more that they found evidence of glaciers, but up in montane areas. Okay, and they were actually found evidence of glaciers in montane tropical regions, much further south than had been previously thought existed. Okay, so things like these striations and these glacial valleys and so on were found, did I say much further south? Much further at much lower altitudes than they occur today. Okay, so the fact that glaciers came down the mountains much more than previously thought, even in the tropics, indicated that temperatures in the tropics were much lower than they are today. Okay, so if temperatures are much lower in the tropics than they are today, then that means that tropical ecosystems boundaries would have been much different than they are today. Okay, so extrapolation of temperature changes in the montane regions to the lowland tropics suggested extreme contraction of rainforest as the temperatures fell, and rainforests in the form of convectional rainfall and so on became much smaller. So rainforests were thought maybe to be broken up into small refugia, and there was a massive expansion of savannas and dry forests in what were former rainforest areas. So these top two pictures indicate the thinking of the tropical refugia hypothesis. So this is the current distribution of rainforests today, and this is the hypothesized distribution of rainforest into these small patches during the height of the last glaciation, where it is the rainfall at the current day is thought to be high enough to support rainfall, rainforest during the last ice age. I'm just going to put this phone on mute. Thank you very much. Okay, so the refugia hypothesis suggested that rainforests were broken up into small patches, and this was taken a logical step further to indicate that rainforests, populations in tropical rainforests were broken up into smaller populations over time, and these smaller populations would have diverged, and so when the warmer weather returned and the rainforest became continuous once more, previously similar species from one refugia would be now different to the same species but evolved differently now from the next refugia. And this was erected as a hypothesis to explain why there were so many species in tropical rainforests. Okay. Further evidence, because this was all based on conjecture and there was no real hard evidence to support the refugia hypothesis, further hard evidence from palynological cores from swamps and so on, where you look at the pollen record and you can tell whether an area was savanna or not by looking at the pollen, showed that extreme contraction of the tropical rainforests did not actually occur. Instead, tropical forest was certainly truncated, but that forest would have turned into tropical dry forest and in extreme places savanna. But the extent of the core areas of tropical forest as we see today remained tropical forest. In addition, it's thought that So rainforests probably did not undergo massive Pleistocene contractions during those Ice Age periods. These Ice Age, so refugia were hypothesized to occur here at these very cool areas, and then the intact rainforest came back at the interglacials. That is thought not to have occurred now, and instead rainforests did contract, but mainly at their margins. So for instance around northern South America, including Trinidad. And it's thought that these rainforests were actually replaced by more dry forests, more deciduous forests, which were better able to survive the lower rainfall. It's not thought that the temperatures fell to any great extent, because as you see today, the temperatures across the tropics aren't really that variable. Okay, so it's looking like northern South America, including Trinidad, was quite a lot of it was dry forest. Okay. Sea level rises were also on the move during the past 10,000 years or so. Analysis of coastal deposits showed that the sea rose rapidly from about 15,000 years before present, after the peak of the last glaciation, and only slowed down around 6,000 years before present, and reached current levels around 4,000 years before present. So Trinidad was in a sea of tropical dry forest around 15,000 years before present, and the northern range were simply a range of hills in a coastal plain about 15,000 years before present, which was contiguous with mainland South America. At around 6,000 years before present, the lowlands between Trinidad and mainland South America had basically filled up with rising sea levels. So Trinidad was basically cut off. Okay, at the same time, the tropical dry forests which predominated were being colonized by evergreen tree species, and those evergreen tree species probably didn't have very far to travel, because they probably came from local refugia such as riparian forests or wetter parts of the landscape where these evergreen species could survive. This is a map of modern day Venezuela. The stippled areas are rainforest, and the clear areas are savanna. This may represent, or may be similar to, the situation which existed during the last ice age. The tropical rainforest species were restricted to along watercourses, and they formed riparian or gallery forests. But with the return of wetter conditions, warmer and wetter conditions, these species were able to colonize the interfluvials, or the areas between these rivers. And as you can see, they wouldn't have very far to go, because they were present along most of these watercourses already. Okay. Ecosystems in Trinidad and Tobago were probably similar to today at around about 6,000 years before present, but with a higher proportion of deciduous trees. It is thought that the northern range, because of orographic rainfall, probably supported rainforest and moist forest, evergreen moist forest, throughout the ice ages. Okay, but the lowlands probably were dry forests with a high proportion of deciduous trees. Because rainfall blown from the east by the trade winds is always going to bring in more moisture, it is likely that the eastern part of Trinidad and Tobago was wetter than the western part and may have supported evergreen forests even back then. Okay? So, humans arrived around the end of the last ice age, and there is archaeological evidence which indicates that humans were present in Trinidad around 8,000 years before present, okay, and permanently occupied Trinidad from around 6,000 years before present. There is evidence of settlements and so on from about that period. Elsewhere in northern South America, humans have been implicated in conversion of forest to savanna. For instance, the Grand Savanna in Venezuela, about 8,000 years, or 10 to 8,000 years before present, when humans first arrived in northern South America, there was a rapid increase in the amount of charcoal and grass pollen in pollen cores. And that is taken to indicate that humans arrived and basically started burning the ecosystems for subsistence purposes, and they basically caused the conversion of forest to savanna. It doesn't look like that sort of thing happened in Trinidad, which indicates, well, at least not on the majority of Trinidad, which indicates that Trinidad was probably wetter than those areas of northern South America. So fires were not as ruinous as they were in northern South America. So maybe there was, because Trinidad is on the eastern coast, it had enough rainfall to support these evergreen forests. Okay, some pictures. First of all, this is a reconstruction of what the land area would have looked like during the height of the last ice age with the lower sea levels. You can see Trinidad there. The green represents land and the blue the ocean. So Trinidad was well within the land at that time, which almost extended up to Barbados. Grenada looks like it was incorporated as well on the continental shelf. So Trinidad was part of the land. Now, as the sea levels rose and flooded these coastal plains, Trinidad became an island. The ecosystems in Trinidad may have looked similar to this and to this, with thorn scrub and deciduous woodland. This is on Shaka Shakari today, on one of those Bocas Islands off the northwest of Trinidad in a rain shadow. This is on Margarita Island off the north coast of Venezuela. This is a picture of the Grand Savanna in Venezuela today. So this area was previously covered in forest and then burnt and converted to grassland after humans arrived. Okay. Alright, so what are the implications of management of this geological history to the current state of tropical ecosystems? Well, the first thing is that tropical rainforest ecosystems are very ancient. They've been around since the Cretaceous, and this may account for their very high diversity. Okay, so there's a long time for mutations to occur and build up. Tropical desert, savanna and dry forest ecosystems are less old and also less diverse. Most, if not all, angiospecies have had their origin in the rainforest, and the current state and distribution of tropical ecosystems is transient. And we can see evidence of that transient nature in some of the species distributions that we have in Trinidad. For instance, sandbox, Huria crepans, is a species of tree which is very much characteristic of dry forest ecosystems around the world. And yet in Trinidad we find that in some of the wettest parts of Trinidad, for instance the northeast coast up around Toco. One of the reasons for that is because that area probably was much drier, maybe 10 to 15,000 years ago. Okay, and maybe the temperatures of the world are changing yet again. They're getting warmer, and that is going to have an impact on the boundaries between these different ecosystem types even now. Okay, so we are actually looking at global warming now, and our next lecture is in fact on global warming. So thanks for that lecture. Bye.